Okay, so maybe we can start the session. Maybe some of the participants can join later. So welcome to the live session for week four for the course Semiconductor Device Modeling and Simulation, which is taught by Professor Vivek Dixit from IIT Kharagpur. And I am Anant Singhal, a PhD student from IIT Jodhpur, and today I'll be assisting you in solving some of the similar assignment problems that have been given to you in the week four assignments. So, we have already, so this is the course outline that we have, and in the previous week, we have covered some of the very basic topic of the device, or not the device, but the material part. So we have seen what is silicon, why do we use silicon in the initial weeks, and how does a silicon structure, the crystal structure of a silicon looks like. Then we also studied how what exactly is a band structure, or what how does a band diagram comes into the picture, and based upon that we studied some of the Fermi-Dirac statistics that is required to solve the carrier concentration, etc., for any material, and in particular silicon for this particular course, because we are dealing with the semiconductors. So for this week, now what we'll be doing in the further subsequent weeks, and this week we'll be starting with one or the other device that we use in the state of the art, I would say, like PN junction, which is the topic of this particular week. So we'll studying the PN junction in this particular week, which is under equilibrium for this particular week. So PN junction is nothing but like we doped N-type silicon, we have a P-type silicon. So now what we are doing, we are kind of having both the dopings in a single bar, and we'll be seeing what happens to the energy band diagram, etc. Then we'll be deriving the IV relation. So I might need to take two classes for this particular topic, because it has a lot to understand. Because before even going into the device, we need to understand how exactly is the band bending happening, or the band structure is going to change when you have two different types of doping in a single silicon bar. Then we'll be studying some of the non-idealities in the p-n junction, which is something like the breakdown and the recombination currents and the generation current, that is basically related to the reverse bias of the PN junction, and some of the transistor configuration that we have. So transistor is nothing but an active device. So it could be a bipolar junction transistor, which is this BJT. It could be a MOS transistor, which is a MOSFET, which is a metal oxide semiconductor. Then we have junction FETs, we have metal MES FETs, and high electron mobility transistors, etc. So yeah, uh, these are all the topics that we'll be covering in these subsequent weeks. And today we'll be starting with the very basic of the junctions. And before going into the device, we'll be studying what exactly and how exactly the junctions form. So let me start with the very basic topic of junctions. So if you remember in the previous class, what we did is we studied about the band structure of a single type of doping. Let's say if it is either N type, or if it is either P type. So, but what do we get to know from the previous class? That from the band diagram, what do we have? What we can derive is we can have the Fermi level. We can know the position of the Fermi level, and by knowing the location of the Fermi level, we can deduct what type of material is it. Is it either N type, or is it either P type? Then we can also find out maybe the electric field, or maybe if you see the electron concentration, you can clearly see whatever the difference in the Fermi level, you can detect whatever the electron concentration is there in the particular semiconductor bar. Then what exactly were we plotting when we are plotting the band diagram is the energy. So we can easily calculate the energy, because we can clearly see the levels, different levels, the energy difference between the, let's say, the Fermi or the EC, or the intrinsic or the Fermi. So this is all that we studied in the previous class, that this is what the energy band diagram is. Now we know that energy band diagram is nothing but the charge multiplied by the potential. So even if we have the energy band diagram, the negative of that is nothing but the potential. So even if we apply some potential, let's say in any device, we can even deduce that what kind of device is that. And even if we have, let's say, two different types of doping, we can deduce by the bending like the electron flow is from which to which type of doping, etc. So this is very important to understand how the band bending is happening. So for that, we'll be taking the thermal equilibrium case, which means that we have not applied any external excitation or any external potential, and the device is in thermal equilibrium. We are just what we are doing is we are taking two materials, or we are taking a single bar in which we are doing different type of doping. So let's take so one key thing that you need to remember is that at thermal equilibrium, the Fermi level always aligns. That means we have a single Fermi level even if you take two materials having different Fermi levels. So if you join them, but at thermal equilibrium, what will happen? That Fermi level will align. So let's take a very basic example maybe that will make it clear. So let's say we have a single bar in which we have, let's say, two material. This is material 1, this is material 2, and let's say the Fermi level for this material 1 is F1 and for this is F2, and let's say the density of states is G1 and the density of states for this is G2. And since now we have already seen the theoretical lectures also, we know that the integration of the density of states with Fermi level is nothing but the concentration of the particular device or the electron. And we know that F1 is nothing but, we have derived this in the last lecture also, it is nothing but exponential of, let's say I'm writing EF1 for this material by KT, sorry, and F2 is nothing but 1 upon 1 plus exponential of E minus EF2 over KT. So now we have already known this. So as I said, we already know now that the concentration is given by the multiplication of the density of states, which I have given as G1 times F1. So if I write in terms of electron concentration of this particular material, it will be G1 times F1. And similarly for the second material, it would be G2 times F2. So now what we need to establish, we also need to establish the whole concentration, because we know that the total overall flux in a material going from N to P or P to N is always continuous. So we need to understand that what is the whole concentration also. So P1 and P2. So anyone having any guess what would be the P1? Because if you remember in the last class, what we studied is F1 is a probability of the electrons getting occupied at a certain energy level E. And we also established that the probability of holes getting occupied is nothing but 1 minus F1, right? So it would be nothing but G1 times 1 minus F1, because this is the probability of any energy level occupied by the holes, because this is 1 minus of that, and the total probability is always 1. Similarly, we can write for P2, it is nothing but 1 minus F2, right? So this is the very basic again. So if I try to now say that we know that the flux across these materials should be constant, right? Should be continuous, not even constant. So what we can say is that the N1, which is the electron concentration going from N1 to N2 should be equals to the ratio of the whole concentration going from P1 to P2. So we can also write this in simplistic term as N1 P2 is nothing but N2 P1. And now if we can feed these values here, so what I can write, N1 was nothing but G1 times F1. P2 was nothing but G2 times 1 minus F2. Then N2 is G2 F2, and P1 is G1 times 1 minus F1. Sorry, this is F1. So if we can clearly see, what I can do is I can cut G1, G2. So what I am left with is F1 minus F1 F2 is equals to F2 minus F1 F2. So again I can cancel these terms, and we have got to know that the probability or the Fermi Dirac function of both these materials will align or will be equal. So now if the Fermi Dirac function will be aligning, so what do we mean by this is, we can say that 1 upon 1 plus exponential E minus EF1 over KT is equals to 1 upon 1 plus exponential E minus EF2 over KT. So what can we deduce from that? Any guesses? So what will be the exact equal term if F1 is equals to F2? Anyone wants to take a guess? So these two needs to be equal. So for this, there is only one term which is different in both of these expression. One is this EF1 and one is this EF2. So this implies that the Fermi level of material 1 will be aligning with the Fermi level of material 2. So that means that the Fermi level always aligns if we are talking about thermal equilibrium. Now there are two, three more technical terms that I'd like to add on over these. So those two terms are, the first is a work function and the second term is the electron affinity. So does anyone know what is work function or electron affinity? Any definition that you might be aware of? Okay, so it is nothing but it is related with the energy levels. So if you remember, let's say this is the band diagram and I am just randomly plotting the EF as of now. I'm not talking any N type or P type particularly. Let's say this is the Fermi level and this is the vacuum level. So the energy which is required, so there are two types of energy. One is which is required to remove an electron from conduction band to the vacuum level. So the conduction band to the vacuum level is nothing but the electron affinity, sorry. So which is this term. So it is denoted by chi. And the energy required to remove an electron from Fermi level to the vacuum is nothing but the work function, which is what we denote as phi. So I'm multiplying by Q just to have the term in terms of energy, and this can also be expressed in terms of voltage, etc. But for now, we are kind of denoting it in terms of the electron volts. So these are the two terms that we have that we also need to be aware of. So by having these concepts, so what we have understood till now that at equilibrium, what do we have is the alignment of the Fermi levels. And from the band diagrams, we can clearly understand the energy values also. So keeping this in mind, I mean, let me give you some more analogy. This is important to understand. So let's say you have a bucket full of water, and the highest level of this bucket is what I'm calling, let's say, at Fermi level 1. And now you take one more bucket, which is let's say this much full, and the highest level of this bucket I'm calling it as Fermi level 2. No, so now what I do is I join these two buckets, like let's say from a pipe, and open these. So what do you think will happen to the water level? Let's say this is bucket 1, this is bucket 2. So anyone wants to take a guess? What will happen to the water level? Will the water level decrease or increase in either bucket 1 or bucket 2? Yeah. So something like this will be going to happen. So it is correct. So since we have a higher level of water in this, so something like this will happen. The water will become leveled, and the water from bucket 1 will flow towards bucket 2 and the Fermi level or the water level will align. So this is the analogy that we have exactly related to the Fermi level. So what I'm trying to say is, let's make a band diagram similarly like this. So let's say I have a band diagram, sorry. So let's say this is EC, this is EV. Let's see, this is EF, and one more material that we have. Let's say for this is EF. So now what will happen? This Fermi level, or let's say I'm also making the vacuum. We've understood that this is the work function 1, which is the difference between the Fermi level to the vacuum. So let's say I'm denoting this as phi 1 and I'm denoting this as phi 2. And we can clearly see that phi 1 is less than phi 2. So like this, what happens? The water flowed from here to here. So here you see the Fermi level, the energy wherever it is higher will flow, the electron will flow from the higher energy level to the lower energy level. This is what I'm trying to say, or let's say we are establishing these two things, that electrons will always flow from higher Fermi to lower Fermi level, or electron will flow from smaller phi to the larger phi. So you see here the work function is smaller as compared to here. So wherever the work function will be lower, the electron will be flowing from that side to the work function where it is higher. So so as the water got leveled in the previous case, which is the water, so what will happen? This Fermi level needs to be come down to have the alignment something like this. So you can clearly see if this whole thing comes down, let's say this particular thing comes down to so that this Fermi level will align to this point. So we need to have some bending for that. Otherwise, it will not come down. So let's say if this whole blocks get shifted and this remains here, so there should be the connection of EC and EV, something like that. So this is how exactly the bending is taking place. So I'll try to explain this is in thorough using the example of the PN junction. So now one more thing that you see is we are not even interested here because nothing interesting is happening here. Only interesting thing that is happening here is at the interface of these two. Because here only the bending is happening, but the substrate part or the bulk part exactly remains the same. So everything that we'll be doing or every equation that we'll be solving will be around this junction. This is what we call as the junction. Hence, we are also very much interested in junctions. Okay, so do you have any idea like what universal equation do we use to have, let's say, the solution of the electric field or the potential? If you have ever worked over even the simulation tools such as TCAD, etc. So there is a universal equation that we are solving to calculate the potential or the electric field. So any idea what is that equation? Okay, so that equation is what we call as the Poisson's equation. So this is the most important equation in whole of the semiconductor physics. As Poisson equation is nothing but the differentiation of the electric field with respect to the position is nothing but the charge density over epsilon. Or we can also calculate the potential because we know that E is nothing but d phi by dt. So we can also write that the double differentiation of potential is nothing but the charge density over. So this is what is happening. So in every tool that you solve or you use, let's say you are solving a MOSFET. So at every point which you have done the meshing, so this every point is actually solving this equation and getting you the final potential of this particular part. So this is how the solution of the in any of the simulation tool happens. So we also need to be aware about the Poisson's equation. So now if I try to, let's say, have a band bending or the band diagram of a PN junction or the for let's say for this particular case. So let's do that. So as I said, let me make it again. This was the EF for this, and let's say this was the EF for this. So can you tell what type of material is this and what type of material is this? Is it P type or N type? Uh, just from this, I can you tell what type of material is this? Yeah, yeah, exactly. Because the Fermi level is close to the valence band for this P-type material, and for the Fermi level is close to the conduction band, so it would be the N-type material. So let me write this as EFP, and I can write this as EFN for clarity. And now what we can see is this is having a Fermi level, higher Fermi level. So the electron will flow from the higher to the lower. the first thing that we have now established is the Fermi level will align at thermal equilibrium. So I can make a single line in which my EF will align. So let's say this is EF. And since the electron will flow from this to this, so this whole thing needs to move down, right? If I try to make the diagram again, so this is ECEV, so this is the P type, right? This will remain same, and the energy or the electron will flow from P type to N type. So this is actually the Fermi level, and this will be the EC, this will be the EI, and this would be your EV. EC, this is EI, this is EV. And now you see, due to this, what has happened? The band bending has taken place. And everything is happening only around the junction. So this is the junction. And in if there is a gradient, so if there is a change in energy, right? So that basically what it indicates that there is some electric field at this region. Because there is a finite gradient from, let's say, higher potential to a lower potential. Is this band diagram clear to everyone? So this is a P-N junction band diagram. Is there any doubt in this, how it has happened, the bending and all those things, or is it clear? Okay, so sorry. Yeah, so I have explained the Fermi level alignment in the starting slides. So maybe you can see that over YouTube. So that is a similar concept. So this only deals that at equilibrium, what do we have is the Fermi level always aligns. So if you already know this, then in this, what I have done is that the only case that I have extracted from the first slide is that the Fermi level will be aligned. That is, it is a single line. So you can see that over YouTube after the class if you have missed the initial 10 minutes. Yeah. The whole point was to show that how does the band bending happen. So if it is clear that it is how it is going downwards, then it is fine. Yeah, so if you have understood like the band bending will happen like this, so can you tell which band diagram is correct out of these? Let's say, okay, so this is N plus, I hope it is visible. This is N and this is P. So maybe you can take 1 or 2 minutes and maybe type your answers in the chat box. It would be good. Think about how does the band will go down or up for the N plus N or P. Yes, sorry. Yeah, only three options are there. Can any of you tell why option A? Yeah, yes, yeah, yeah. Okay, yeah, that is the correct explanation. So option A would be the correct answer. That is true. So the whole point here was since we have a higher concentration of N plus, so the Fermi level will be very close to the conduction band. And the band bending we have just seen that, let's say, I'll use these cases. So let's say this is the Fermi level for the N plus, and I'll make another one, and this is the Fermi level for N. So you see the Fermi level. I mean, the electron flow will happen from here to here. So for this needs to go down, right? So let's say this remains here only, and this goes down. So what will happen? So if I need to align the Fermi level, this will remain here, and I mean, yeah, this will go down, sorry, and this will remain here only. So yeah, this will be the EI, and this will be the EV. So the band bending will take something like this for the N plus case. So this is N plus, this is N, which is exactly happening here. So the correct answer would be option A. So that is true. So I hope you have all understood the concept of band bending now. So if you have all understood the concept of band bending, I think we can move towards the PN junction, because this is exactly the band diagram of the PN junction that we have just understood. So let's see what exactly or how exactly does a PN junction diode works. So in very layman terms, you have understood or you might have heard about a diode, that a diode is a unipolar device that only allows the current to flow in a single direction, and it blocks the current into the opposite direction. That is, it provides zero resistance in one direction and it provides infinite resistance in the other direction. This is how we understand diode in terms of, let's say, a circuit level or a symbol level definition. But what exactly is happening in diode as a device? So that is what we are seeing. So diode is nothing but, let's say we have a single silicon bar, and at one side what we do is we dope it with a very high p type of impurities, and in the second side we dope it with a high n type of impurities. So it is a single bar. You need to understand that we are not joining two different bars of let's say a p and n type. It is a single bar in which we are doing the both type of doping. So that is the one main thing that people misunderstand, that we are joining two types of bar. That is not the case. So now we have p type. So p type, what is the majority carriers? Can anyone tell? Yeah, so holes are the majority carriers. So what we'll have, the minority carriers will be the acceptor ions, right? Because holes are the majority carriers. So this is the acceptor ions which are minority, and holes is, let's say I'm defining this as something like this. The blank or the hollow circles are holes. And now in the n type, the majority carriers would be electrons, right? So the minority carriers will be the acceptor ions, sorry, the donor ions, not the acceptor ions, which I'm denoting by plus charge. And let's say we have a lot of electrons, which are the majority carriers. So let's say as soon as we dope, because we have a lot of electron here and we have a lot of holes here. So let's say as soon as we dope a single cluster having, let's say, p type at one side, n type at another side. So what do you think will happen as soon as we dope these? What should be the first thing that should happen if we dope it like that? Yeah, diffusion happens. So in very basic language, what will happen? This electron will try to be attracted towards the holes, and these holes will be try to attract it towards the electrons, right? So this is what is diffusion. So let's say we have a doping of Na, because p-type is acceptor ions doping, and let's say I have a doping of Nd here. So what happens is these free electrons, whatever the free carriers, they will try to have diffusion, or they are try to move from a higher concentration to the lower concentration, and there would be some recombinations also, because this electron can get merged from this hole and it can recombine into a neutral electron or a neutral atom, not the electron. So there, one thing that the first thing that will happen is the diffusion. So let's say I've taken a case in which Na is having some certain, let's say 10 raised power 16 value, for example, and Nd is, let's say, 10 raised power 15, for example, as of now. So what do we see here is there is a abrupt concentration change at the junction, right? So this is the main point. So what we study in general is the abrupt p-n junction diode. So this is one assumption that we take, that the concentration gradient is very abrupt at the junction or very abrupt at the interface. So this is the actual case, and what happens, as you have said, the hole will try to diffuse from here to here. This is what I am calling as hole diffusion, and the electron will try to diffuse from the n side to the p side. So this is what I am calling as electron diffusion. And diffusion is nothing but the moving of electron from higher concentration to lower concentration. Is this thing clear? The hole and the electron diffusion. So yeah, so my question now is, let's say the electron and holes are diffusing. So is it infinitely possible to have the diffusion? even without applying any bias? Will it happen infinitely? Yeah, so once we have a lack of free carriers, that is, let's say once we have a diffusion or once we have the concentration equal at both the sides, so the diffusion will stop. So what will happen at that point? So let's say diffusion happened. So now what you will see is we don't have any free carriers left at the junction. So let's say this was P type. So let's say here the acceptor carriers were there. This was N type. So let's say the donor ions are there. And I mean here also it is there, but here could be there could be some of the left of the holes or the electrons. But you will see what majorly you will see is that we have a region in which there are no free carriers after the diffusion happened. So now what you can clearly see is this area is depleted of free carriers or even the carriers. So hence what do we call this region? Do we call this region as a depletion region? And depletion region, what do we have? We have a higher potential to lower potential, right? There should be an electric field that should happen from higher potential to the lower potential. Is this thing clear to everyone? Yeah, so one more thing that we just saw. So this was Pn, and we just made a band diagram if you remember, and it was looking something like this, and then this, and then this, and then this. So the electric field direction, you can just directly judge from the band diagram that it is always up the hill. That means wherever the band diagram is going upwards is the electric field direction. From for this case, it is from right to the left of the screen. I hope it is clear to everyone. So let's try to have a very basic understanding of some of the key terms of the p-n junction diode. So the first would be let me make a quick band diagram. So I'm still talking about equilibrium only because we still have a Fermi level which is clearly aligned. So this is the Fermi level, let's say. This is EFP side, this is EFN, this is ECN, this is EVN, this is ECP, EVP, and this is EIP and EIN. So what we need to ensure first of all, whatever the change in the EC profile is exactly the change in the EI profile also. So this is and this is both same. And whatever this potential that is being changed inside the depletion region is what we call as the built-in potential, and we denote this as VBI. So this is nothing but the built-in potential. So this is again nothing but the built-in potential. So if we try to find the value of this built-in potential, like what exactly is this built-in potential or the barrier that is being created? So if you remember in the last class, we written the four formulas to calculate the difference between the energy level between the Fermi and the intrinsic, or the conduction and the intrinsic, or similarly the valence and the intrinsic. So let's say this, I'm calling this as Q phi P because this is the P side, and this is what I'm calling as Q phi N because this is the N side. So from this diagram, what we can clearly see is VBI is what in terms of Q phi P and Q phi N. It is nothing but Q phi P plus Q phi N. Is this expression clear to everyone? Yeah. So can anyone tell how can we find the Q phi P? We have written some formulas in the last class if you remember. So can someone tell how can we find the difference between the Fermi level and the intrinsic level? Yeah. Yeah. So if you remember for phi p, we wrote that n, let's say if I'm talking about p type of semiconductor, because phi p is p type, so we have this formula p is equals to na exponential of ei minus ef over kt. For this particular case, p is nothing but na because we have a p type of doping, ni exponential of EI minus EFP is actually this, if you see. So I can write this as phi P over KT, or I can even write Q. So from this, we can clearly write the phi P as, if I take log on both the sides, so it would be KT by Q ln Na over Ni. Similarly, we can write the phi N also, which is nothing but, how can we find? Ni exponential of EF minus EI over KT. And you can clearly see EF minus EI in the N is nothing but phi N. So I can write this as ND because N is ND here, exponential of Q phi N over KT. And this will give me phi N as KT by Q ln ND over Ni. Is there any doubt in this? Anyone? So now what? How we included VBI? VBI was nothing but phi P plus phi. So can anyone tell what will be the final value of VBI? Yeah. So it will be multiplied, right? So ln A plus ln B is nothing but ln, yeah, 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 Na ND by Ni square. So this is the built-in potential that we calculate. So since we have a Q in there, so this unit will be volt. We can calculate this in volt or electron volt. So this is the built-in potential that we have. So let's have a very quick numerical, I mean a very easy one maybe. Hmm. So let's say I'm giving you a PN junction in which the P-type doping is given as 3 times 10 to the power 16, and type of doping which is given by 2 times 10 to the power 15. So this is all in per centimeter cube. And let's say I'm also giving you Ni, which is 1.5 10 to the power 10 per centimeter cube. And all of this is happening at 300 Kelvin. So calculate VBI. So this is the question. Take maybe 1 or 2 minutes and let me know the answers in the chat box. Sorry, it seems to be on the higher side. It should be in some milli electron volts. What did you say? 6.8. Yeah, so KT by Q, if you need to remember the value, this, yeah, 0.026 is the value, not 0. So this should be 6 times 10 to the power 31. This should be 2.2. Yeah, so it should be 0.68 volts. 6.8, no, but 0.68. Has everyone got this answer? Any doubt in this? Okay, I hope not. So now what we established what is the built-in potential. So we have already seen that we use Poisson equation to have the calculation of electric field or the potential, right? So now what we'll do, we'll try to calculate the electric field. So what is the Poisson equation? I just wrote it is nothing but dE by dx is nothing but rho v over epsilon s. So rho v is nothing but the charge density, which is nothing but coulomb per centimeter cube. So let's say if I try to do that, this is p type, this is n type. P type, what do we have? We have the acceptor ions, right? And n type, we have the donor ions. So now if I try to make a diagram of charge density, this would be, let's say, the position. So here what do we have? We have the positive donor ions, right? So the density would be charged into the donor ions, right? And this is a positive ion, so I can write this as something like this. And the density on the p side would be negative because we have the negative acceptor ions, and let's say this is the constant density. So this would be minus q and a, this would be q and d. Is this clear to everyone? The charge, oh sorry, the rho v plot. So this is y-axis is the charge density. Please let me know if you have any doubt in this. No, no, the Poisson equation we will use to derive the electric field. Yeah, so now we have, yeah, sorry, electric field only. So we will find, yeah, electric field intensity and electric field are the same thing. So we call sometime it as electric field intensity or electric field. So it both are having the unit of volt per centimeter only. So we'll find the electric field from this because I mean initially what I was trying to establish what is the value of rho v. So now since we know rho v, we can integrate this at both the sides and we can also find E, right? Is it clear? So E will be nothing but the integration of rho v over epsilon s times dx. So now what we have done is we know that at p side. So this is what I have written as xp. So this is the p-type depletion region and this is xn, which is the n-type depletion region. So let's say I'm talking about p-type first. So let at minus x, let's say from 0 to minus xp, which is this region, this black that I'm shading right now. So what do we know? That rho v is nothing but what? What is the value of rho v in this region? Anyone? This is quite straightforward. You can see it in the diagram. What is the value of rho v? Yeah, it's minus q into Na. So what we can do is electric field will be nothing but integration of minus q Na over epsilon s dx. So what will be the integration of 1? It would be x, right? So it is nothing but minus q Na over epsilon, which is constant, times x plus some constant c1, let's say. Is this clear to everyone? Yeah, so now what the main thing that I said previously was the electric field is only present at the junction. So it would be zero outside of these two things, right? So here the E is zero, here the E is zero. So I can say that at x is equals to minus xp, the electric field is zero to calculate the constant. So I can write 0 is equals to minus q Na, x is minus xp over epsilon s is equals to c1, sorry, plus c1. So c1 will be equals to minus q Na xp over epsilon s. And I can keep this here to calculate the final E, which will come out to be q Na, sorry, minus q Na is happening. Which, no, no, so there are two negative signs. One is minus q Na and one is minus xp. So both of them will cancel, and if it comes this side, this would be negative. So it would be minus qn if I take common x plus xp. And this is only valid when x is from minus x to 0, minus xp to 0. Is this clear to everyone? How this has come? Any doubts? Okay, so can you quickly tell what will be the electric field when x is between xn and 0, positive side? So rho v will be q and d, right? Yeah, so what will be the E? Okay, so if we solve it, it will come out to be q and d over epsilon s x minus xn. So now what we have got, yeah, we have got the electric field at both the sides. So if I try to plot it on the x-axis, so what do we got? Let's say this is minus xp. So I'm making a very This enlarged diagram. So let's say this is minus xp, this is xn. So after this, the electric field has to be zero. This is what we already know. And from p side, what we know is, let's say this was the p side. So at s equals to zero, which is this point origin, our electric field will come out to be minus qna by epsilon s, right? So this value would be qna over epsilon s, or if I even keep x zero here, so it would be minus qnd over epsilon s. Sorry, it would be xp also and xn also. So this is the maximum field, and this is how we see a linear relation because it is a function of x. So this is a plot of electric field. Is this clear to everyone? Any doubts here? Yes. Okay. Yeah, yeah. So you have understood that how these equations have come. So if I try to write this as a linear function, which is let's say something minus mx plus c, right? So the intercept would be if I keep x equals to 0 because it is this point, right? So it would come out to be E is equals to q n d minus xn over epsilon s, right? So this would be the intercept which I have marked here. And we have a straight line from passing this point to this point. So this is I have just joined. Similarly for, yeah, this value would be this. And these both, yeah, it is minus, right? If you keep x as 0, this minus will come out. Yeah, so minus. That is why I have given the negative value, right? I mean, what is the doubt? It is in the negative x direction. This is 0, this is negative value. Yeah. So what we can clearly see from this is the q na xp over epsilon s is equals to q nd xn over epsilon s, right? That is the value at 0. So this what it gives it naxp is always equals to ndxn. This is a very important relation that we use in a lot of numericals. So whichever side has a higher doping. So for example, let's say Na for example is 10 raised power 17, Nd is equals to 10 raised power 15. So which one would be bigger, xp or xn? Can you comment using this relation? So xn would be greater, right? Because we have two orders lower. So you need to always see that whichever side has a higher doping, the depletion region would be smaller in that. For example, let's say as I am taking, let's say this is the P side which is 10 plus 17, this is 15. So depletion region would be smaller here and greater on this side. So this would be the depletion region. Is it clear to everyone? Minus XP and this would be XN. Okay, great. So if this is clear, then again, so what was this? This was the integration of the charge density. Now we know that V is nothing but the integration of electric field, right? So we write E as minus dV over dx. So I can easily write V as integration of E over dx. So I can now integrate this once again. Where is it? Yeah, integrate these two equations once again to get the final voltage. So this is a function of x. So what will be the function of V? Similarly, integration of x would be anyone? No, x would be no, not ex. So E itself has a value now, which is q n a. Let's say for p side x over d epsilon s dx. So integration now we need to do of this. This is still a constant. Yeah. So if you try to calculate the phi, it will come out to be QNA. I'm writing directly because this would be, so it will come out to be x plus xp whole square. And for p side, so this is when x is less than, and when x is between 0 and xn, this will come out to be something like QND over epsilon s xn times x minus x square by 2 plus QNA xp square over 2. Sorry. So you can do the integration by yourself at home. So this will be the final function, and the main thing that we are uh, trying to establish here is this is a parabolic function. So that is why if you see whenever I made the band diagram, this is parabolic in nature. Yeah, these. So this is parabolic in nature. And voltage is nothing but, or the energy is nothing but minus QV. So it is inverse parabola. You see, parabola is something like this, and this is the inverse of that. Is this clear to everyone now? How the band diagram and these all are related? Yeah, so I'm just integrating. So x, if you integrate, it would be x square by 2, right? And then we'll apply the same condition that at x is equals to minus xp, we have a potential of 0. Then we have applied at x is equal to x and we have a potential of VBI. Let me try to make the band diagram, you will understand. So what we started with is this. So we had this, let's say this is Q and D, this is Q and A. Right, so this was the rho v, and we integrated it once. We got the electric field, which is something like, so it is 0 here, it is linear here, it is linear here, it is 0 here. This is electric field. Similarly, if I integrate it once more, it would be parabolic, right? This is what I was trying to say. So it would be something like this. So this is again 0, sorry. And then this value is what we have the built-in potential. So this is again minus xp, this is xn. So we have just applied the conditions here. And from this you can get this integration. You can try it out at home because otherwise we will not be able to solve any problem. But I hope you have understood the main point was that this is the integration of this and this is the integration of this, and hence why the band bending is happening in a parabolic nature. Is this thing clear to you? Yeah. And here we can clearly see that at x equals to xn, we have VBI, which is okay. So we can also calculate VBI by keeping x equals to xn here, right? So let's calculate the VBI. So we already have a formula of VBI, which is nothing but KT by Q ln NA over NI square. So if I try to calculate VBI from this formula, which is this formula, so what I'll do is I'll keep x at, sorry, I'll keep x equals to xn. So this will be xn square minus xn square by 2. So this will become xn square by 2, right? And similarly, yeah, this will remain the same. Is this thing clear? I have kept x is equals to xn because at x equals to xn, v is equals to vbi. Is this thing clear to everyone or are you getting confused? Hmm. So that would be xn square by 2. Yeah. So if I try to write, so it would be q by 2 epsilon s. So 2 have taken outside, so it will be nd xn square plus na xp square. So this will be the term that will come out. And we already know that naxp is equals to ndxn. This we have just established. So I can write xn as, let's say in terms of p, I can write it this as na over nd times xp. So I will put this xn here now to calculate the final VBI. So I mean this would be the one formula for VBI, this would be the one formula for VBI. If you're trying to use any one formula, that will work. So what I can write now, VBI is nothing but q by 2 epsilon s. So I'm taking xp square common because I'm using this value now. So it will come out to be na square over nd plus, here it will be only na. So now what I can do is, so I can write this here. So this will be 2 epsilon s VBI over q. It would be xp square, and if I take even the LCM, it will be nd Na square plus Na and D. And from this I can clearly write xp as under root 2 epsilon s Vbi over q, and D will come here. And I can also take Na common from this. It would be Na plus Nd. So that would be 1 upon Na plus Nd. Yeah. So this will be the depletion width on the P side. Is this thing clear to everyone? This derivation? Yeah. So similarly, you can also find Xn, which is exactly the same. It would come out to be Vbi over Q. It will come out to be NaNd over 1 plus Na plus Nd. And from this, you can calculate the actual final depletion width, which is nothing but W, which is Xp plus Xn. Yeah. So that would come out to be, if I just write the formula, I mean, you just need to add these two. It will come out to be 2 epsilon s Vbi over Q. It will come out to be 1 by Na plus 1 by Nd. This is the actual formula, and you need to just be aware about the unit. So if this is in per centimeter cube, this will come out to be in centimeter only. The doping is in centimeter. Are all these formulas clear to everyone? Okay, so let's try a problem of what we have done till now. So let's say we have taken an abrupt PN junction only. I'm giving you some values. Na, let's say I'm giving you 10 to the power 17 per centimeter cube. And D, let's say I'm giving you 5 times 10 to the power 15 per centimeter cube. Temperature, let's say still take at room temperature. Ni, you all know, it's 1.5 times per 10 per centimeter cube. So using this, there are 5 tasks that you need to do. First is to sketch the equilibrium band diagram. So you can do this later. I mean, band diagram we have already seen. So second thing is you need to calculate EF on each side of the junction. Then third is to calculate the VBI. The fourth is to calculate the XN and XP. And fifth is the total depletion width, which is W. And last is the Emax. Emax is nothing but the electric field at x equals to 0 that we just saw, where it was showing the maximum value. So what you can do, you can do the easier things first. You can find me the VBI. You can write that in the chat box, X and XP, W, and Emax. And this you can draw at your homes and maybe send me over email. I'll check. So let me know what is the value of VBI, XN, and XP, or the depletion width you are getting. Is it fine? Are you all trying? Is there any doubt in the question? Okay, sure. So give it a try and let me know. Okay, so 0.68, if I remember, it was for the case when we have 17 and 15, so it should be something different for this. Please check again. This is a different problem that was before given. Okay, zero point 0.7 exactly you are getting? Okay, so let's try it out. Let me do it side by side. So, so to first calculate the VBI, we'll have phi p and phi n, and then we can calculate, or we can calculate. Sorry. So VBI is nothing but KT by Q ln NA and D over Ni square. So we have every value, so it should be 0.026 ln. So this is 5 times 10 to the power 32. This is 2.25 10 to the power 20. So this is something 12. 25, 20, 25, 19. So this is approximately 10 to the power 12, something 1.1. So if I try to calculate this in the calculator, I'm getting 0.739 electron volt. Is it the case with everyone? Yeah, so you can check your calculations if it is not exactly coming out the same. So now the second thing that we can need to calculate here is XP and XN. Let's quickly do that. So now one thing that you see is in the question NA is greater than that of ND. So what will be greater, XP or XN? E. So P has a higher doping, that means the depletion width will be lesser on that side, right? So yeah, XN would be greater. Is this clear to everyone? So let's try to find XN. So it will be 2 epsilon s. Epsilon s is 11.7, 8.85 transfer minus 14 in centimeter by Q, which is 1.6 transfer minus 19 into VBI, which is come out to be 0.739, then N A by ND, which is something like this, N1 plus NA over ND, NA plus ND. So this is a big calculations actually. So this is 10 to the 5, this is 2, so 7 is there. Okay, so you try to fill this will be this 11.7 times 8.85 into 10 to the minus 14. This is the relative permittivity and this is the absolute value. So this will be minus 7, 8.85, 0.739, this is 1.6, this is 5, this should be 1.05. Okay, sorry. Action will come out to be So I'm getting 4.25 to 10 to minus 5, and this is by default everything is in centimeters, so that would be in centimeter, and I can write this as 0.425 micrometer. You can check the calculations again, maybe I have not. So XP, if I try to calculate, this will come out to be 0.02132 micrometer. So you can clearly see XP is at least one order smaller than that of XN. And the final depletion word would be XP plus XN. And this should come out to be something 0.44 micrometer. You can also do it in your homes to get the final answer. So we have calculated VBI, XN and XP. And E max is nothing but, again, the direct formula we can calculate. It is QNA by epsilon S. So I've done the calculation of that too. It should come out to be 32.944 kilovolt per centimeter. So you can take a screenshot of these answers and check it after the class. You can try it out. And this is the question. You should also, I mean, this year could be the homework. You can also sketch the band diagram and find the value of EF on both the sides. And this you can send me over email. So my email ID I will write quickly. So this is my email ID .6@iitj.ac.in. Is it fine with everyone? Okay. So let's quickly do one more problem maybe. We still have some time. So let's do a very conceptual thing now. So let's say what I'm doing is now I'm taking a n plus n device. That means not p-n junction but a n plus n junction. And what I'm giving you is nd1, which is stands for 18 per centimeter cube, and let's say I'm giving you nd2, which is stands for 15 per centimeter cube. And ni, for example, for simplification, let's take n stands for 10 per centimeter cube. Temperature is still 300 Kelvin. You need to calculate the VBI. Don't blindly go towards the formula. So for this question, what you should do the band diagram first and then try to calculate or derive the formula of VBI. You will see something interesting here. So maybe take 2-3 minutes and let me know if you have got some formula. Yeah, so okay. So what I'm trying to say, let's say we'll make the band diagram. So one is N plus, which is this, having a EF. So this has a ND of 10 per 18 per centimeter cube. And then I have taken one more device, which is let's say EF here only. And this has a ND of 10 per 15 per centimeter cube. So what I want to find you is VBI. So PN junction, it was, if you remember, KTLN NAND by NI square. But there is no NA in this device because both are N type. So you need to derive the formula and then give me the value of VBI. Is the question clear to everyone? Okay. Yeah, bending will happen because there is a concentration gradient. How will it happen? That is what the question is. I mean, you need to see how this electron will go from here to here, higher Fermi to lower Fermi. If you can make the correct band diagram, you will be able to know what is the actual value of VBA. That is the main question. If you have understood the concept of band bending, then you should be able to make the correct band diagram. This is what I'm saying. So try to make the band diagram and then derive the formula of VBA. And let me know that formula if you have got the same. Otherwise, I'll also do the same. No answers? Okay, so let me make the band diagram, maybe that will help. So as I said, the electron will flow from higher Fermi to lower Fermi. So this is, let's say, n plus side. So the Fermi level should align. So this is at EC at n plus. Now, since higher to lower, so this needs to go down, right? So this would be something like this. Now what you see here is the band bending will happening like this. This is what we already see in that problem that you give answer to option A. Now the whole thing here is this band diagram. The bending is, this is the built-in potential, which is actually this. This is the built-in potential. And now here if you see, this is Q51 and this is actually Q52. Is this clear to everyone, the band diagram? Any doubts here? So what I am saying is, this is the Fermi level which is close to the n-type, which is here. So the electron will flow from the energy level which is higher, Fermi level which is higher than that of this. So this needs to go down. So I've just pushed this down. So this is the Fermi level that is aligned now, and this is the band bending. So now this band bending is actually the built-in potential, right? This was the same in the p-n junction case. But and the band bending here now, my point is, so this is EI, this is EI, right? EI minus EF was Q phi n for n case, and let's say I'm writing Q phi 1 and this is Q phi 2. This is EI minus EF only. Is this clear? So what will be the value of VBI in terms of phi 1 and phi 2? This is the question. Anyone? It should be phi 1 minus phi 2, right? Phi 1 is bigger. So till now for the p-n junction, if you remember, what do we get? We get phi p plus phi n, right? So here the whole catch was we are getting a minus. That means even if I write phi 1 as, which is the formula ln nd over ni, so phi nd 1 over ni, this is minus kt by q ln nd 2 over ni, right? So this will actually give me the formula, which is, what will be the formula? Ln, yeah, exactly. So whatever is higher will come up. So it is actually not dependent upon an I square at all. This is what's the catch, was the question. So now since we have the formula, so the answer would be kt by q. So the higher one was 10 per 18, let's say, and by 15. So it should be 0.026 ln 10 per 3, 3 times this and then 2 times gamma. So it should come out to be 0.1726 volts. Is the concept clear to everyone? So this is a n plus n junction. So since we have only covered the first topic of this lecture actually, so if I go back, so this is the only thing that we have covered. So we need to do the derivation of IV and all those things. So week 4 and week 5 will be a bit of mixed lectures. I mean, we can cover week 4 and week 5 together. So in the next week, I'll be starting with the derivation of IV. Maybe we'll see some forward and reverse biasing of a diode, and then some of the BJT configurations, and then move ahead like that. So if you have any doubt, you can ask. Otherwise, we can wrap up the session for today. Is there any doubt? The main thing was to explain this particular band bending. So in the next class, we may start with a P minus band bending to have this concept more clear, how this minus came. And till now, I'll also wait for the sketches of the band diagram of this question. You can send me at this email ID, and then we'll see further what we need to do. So if there is no doubt, I think we can wrap up the session. Please let me know if there are any doubts. Okay, okay. So did you solve? Yeah, sure, sure. You can do that. I'll check. Actually, yeah, actually there is no WhatsApp group as of now that has been formed this time because the participants are lower. Yeah, yeah, I saw that, but there is no WhatsApp group that has been made. So you can maybe send your queries over email. I'll try to answer them as quickly as I can.